Welcome to Data Science with EJD. Just like I said in this video, we'll be starting with classification algorithms in supervised learning. As the name implies, we are classifying stuff with these algorithms. So the first one I'm taking is the KNN, which is K nearest neighbors. So and the learning outcome we expect by the end of this session, you want to be able to explain how the K nearest neighbors algorithm works. You want to implement KNN from scratch and using scikit-learn, then apply KNN to classify flowers in the iris dataset. We've been working with this iris dataset a lot. Then you want to evaluate model performance and tune the hyperparameter K. So let's get into it. So conceptual explanation of KNN, right? K nearest neighbors is a supervised learning algorithm used for both classification and regression tasks. So when we get to regression, we can still use KNN. But the approach, of course, will be different, but it's the same basic concept. Now, it is an instance-based when an instance-based learner is actually a lazy learner. That's the idea, right? Like you have to go. Uh, of course, an instance is just a row, so no explicit training phase is required. So you just go row by row to do what you have to do. That's what the idea is. Then how does it work? All right, how KNN works? Um, in step one, it's to choose the number of neighbors. Okay, so and you can set that in your algorithm, right? So if you want, say you have one, you have one, you take the first person so to speak, and then you want to see how many neighbors do you want around this person. Do you want three, you want five, you want seven? You do that. So once that is done, then you measure the distance between the new points and every point in the training data set, right? So you pick a point and pick all the neighbors you want. Maybe you want five neighbors. You now measure the distance from that point to all the five neighbors. If you pick five, if you pick three, all the distance from that point to all the three neighbors. Then the next is you now identify the K nearest neighbors. That is the K points with the smallest distances. So the smallest distances you identify them, and then the fourth step is to classify. So if you are doing classification, you predict the most common class among the neighbors. And then for regression, you predict the average of the neighbors' values. So, for regression, now you're getting a value. So you're taking average of the closest neighbors. For classification, you're predicting the most common class among the neighbors. That's the idea here. So now, see, you can see it's about distances, right? Because when you talk about a neighbor, you're talking about you and the people close to you. So that it's a distance metric. So for continuous data, Euclidean distance is the most common. So if you have continuous data like the iris data set, we have like some of the lengths are in 5.3 and things like that. So you use Euclidean distance, and this is a very common thing in I think is it coordinate geometry now. So you want to talk about the distance between x and y. So it's simply x minus y. But here for Euclidean distance, it's square root of the summation of all the possible distances. So you have your point and then every other point that surrounding it. So you sum up all the square of those distances and find the square roots. That's Euclidean distance. So you have other options like the Manhattan distance, which is just summation of the absolute value of the distances. So you find the distance between the points you picked, and every other one around it, and then you sum them up, and like that. That's your Manhattan distance. And there's a Minkowski distance, which is generalization of both Euclidean and Manhattan distances. Okay, so the next thing is you want to choose your K. Of course, the K is the hyperparameter. So small k, like k equals like you're picking just one neighbor. If you pick one neighbor, it is sensitive to noise because it has high variance. If you pick large k may smooth over class boundaries because it has high bias. So if you have too many neighbors, right, you can have high bias. Then the best thing is to choose K via cross validation. You can do that that's a way of making sure you pick the best you should pick. Then what are some advantages and limitations of K nearest neighbors? Uh, Advantages: it is simple and easy to implement. No assumptions about data distribution. You don't have to worry about the data distribution. It naturally handles multi-class problems. If you have multi-class problems, you can easily take care of them. But for limitations now, it's slow for large data sets. It is sensitive to irrelevant features, and it requires feature scaling. So it's slow. It's slow for large data sets. sensitive to irrelevant features, and requires feature scaling. So you need to scale your features. So if you're working with large data sets, k-nearest neighbors may not be the best algorithm for you. So you may have to think of things like decision trees or random forest, as we're going to see later. And they are very sensitive to irrelevant features too. So irrelevant features can affect how things work and all that. So when do you use k-nearest neighbors, right? The first is when interpretability and simplicity are important. So if you want to be able to interpret your result properly, so you can use, and you want simplicity, so k-nearest neighbor works. Then when the data set is not too large, so if you have, data set that is not too large, maybe it's not in the millions or hundreds of thousands, maybe, the k-nearest neighbor can work. Then when you expect local decision boundaries, you should use k-nearest neighbor. So now, let's talk about K-nearest neighbor implementation with scikit-learn. So first, you want to import the required libraries. Of course, you know the basics. NumPy as NP, pandas as PD, matplotlib for visualization. Then you have scikit-learn now, which is the main thing now. So scikit-learn the data sets. From there, you are importing iris data set. The model selection, you want to do your train test splits. This is the function for choosing for doing your splits for of the data. sklearn preprocessing, you want a standard scalar. Then for neighbors, now you want k-neighbor classifier. K-neighbors classifier, then you have sklearn metrics. Since you're doing a classification job, so you need things like accuracy score, and you also want your classification report. So the next thing you want to do is to load the iris dataset. Now we've worked with iris dataset a lot, right? But I mean, I went the extra mile here to be sure you still see the rows and columns. As far as machine learning is concerned, they don't care about the rows and columns. They just care about preparing the data in such a way that it works very well with the algorithm you are using. Okay. So here now we have loaded the iris here. We have brought it up from here. So we just give it a variable name. I think it's better to label as usual the line numbers, okay, for easier referencing. So you want to load the iris dataset. So in line 2 you have the variable name iris, and then you say load iris. Then you want to create a data frame with feature names. So you want to see the features. Don't forget the features are the inputs that determine the outputs. So, and then you create a data frame. Of course, you need pandas for that. So that's why we we imported down pandas in line 2 up here. So pd.data frame, then you have data iris.data, then columns iris.feature names. All right. So then here you add the target column. So the target column is so you have df target equals iris.target, right? And then you can view the first few rows. Or I mean, to view the first few rows, usually what you do is you put df.head, right? So and it spills out. Oh, okay. I think the problem here is I did not load these things. Yeah, that should be done first because pandas, for instance, and every other thing depends on that. So now that that is done, we won't get this error anymore. Okay, so you can have error for not loading the necessary libraries ahead. So now we have the first few rows. Or the first few instances. For me, you can even do this. So it shows you the first five and the last five. So you see the targets are zeros. The first five target. Well, I mean, the iris data set, don't forget, has 150 data points, right? I mean, it's numbered from 0 to 149. So the first 50 is target 0, the next 50 is target 1, and the last 50 is target 2, as you can see from here. For instance, now, what if I do df.head and I want to see the top 50? You see, that is all zeros, right? Zeros all the way for the top 50. Then what if I do tail instead of head? Now I do tail 50. All right. Df.tail 50. So it shows us the last 50, and that's target 2. So the target thing since we are doing classification here, the target thing is not it's just for categorization. So it's not a number per se that you work with like that. Okay. So we have this. So here I just want to visualize so here now I'm saying the iris data, which are the features now, will be x equals iris data and iris.data. So it has been prepared that way already inside scikit-learn. Then y is the iris target. Those are your labels now. So if you run this, it's done. So I just want to see them. So I have this. So just like I said, right, for machine learning, the data has been prepared in this way. You don't have to we don't care about the label column names and all that, like in when we're working with pandas. So, but I mean, for the sake of bringing back the pandas memory, just to see what the column names are, that's why I did this. But for in machine learning, they don't care so much about that. Just put the features together. Then for the label, for the labels, we have this now. Okay, so each of these features is matched with each of these labels. So you can see the top first 50, you have zeros. Next 50, you have ones, and the last 50, you have two, because you're dealing with categorization here for the three different what are they called now? Species, right? So the next thing you want to do is to pre-process the data. And how do you do that here? You you have you want to split into training and testing sets. You want to use the 80-20 split. So you have the X train, X test, Y train, Y test, and that's equal to that function train test split that was uploaded from here because we need it for that in line 5. Train underscore test underscore split. So you use it to split into train and test. So and then you have the features, then you have the labels, and the test size is 0.2. So by doing this alone, you automatically are saying that the train size is 0.8 and the random state is 42. That's to make sure that the results are the same. If you run it as many times as possible, it's always the same. Then we also want to do some pre-processing, like you want to standardize features. So, and this is important for distance-based algorithms, of which K nearest neighbors is a distance-based algorithm because you're talking about distance of 1 point from all the number of neighbors you have chosen. So you have a scalar and you call the scalar standard scalar. Then for X train, now you scale it. So you say scalar dot fit transform X train, X test, scalar dot transform X test. So by doing this now, you scale all this, right? So the next thing you want to do is to train the KNN classifier. So for instance, how many neighbors do you want? So here we are picking three neighbors, k equals 3. And then the model you're picking, just like when I did that linear regression snippet, the model there was linear regression. Here it's k neighbors classifier, and you have n underscore neighbors to be k. So you're picking three neighbors. The model dot fit. So this is where you actually train your model, right? So X train, Y train, model dot fit. You're fitting them with k neighbors classifier with three neighbors, right? So you run this, and then this tells you it's done, right? So this tells you it's actually done. So here you see, okay, it's fitted. Then if you click on this now, it shows you the documentation for the K nearest neighbor classifier, which is under Scikit-learn. So it shows you the whole background of all of this. So if you're interested in really getting to the bottom of some of these things, you may want to try that out. So back here, so now we have trained the KNN classifier. So the next thing we want to do is we want to now predict. So your model is set. As far as this is concerned, your model is ready. Okay. So once you do the fit, you're done. So the next thing you want to do is you want to try the model to see the kind of result it gives. So see this now. So you want to now, so since your model is ready, you can now make predictions and evaluate how accurate your prediction is. So you now say y pred equals model dot predicts. So predicts now is is a function inside the model you're using, which is k neighbors classifier in this case. Uh, right. So you now want to test with the 20% test you had reserved before now. So and then you're doing evaluation. So for the evaluation, you want to print things like accuracy score. So you want the accuracy score for Y test and Y pred. So what's the difference? Like how accurate if you compare the two? Then you also want to have the classification reports. So classification reports, Y test, Y pred, target names. You want iris target name. So for the target, so you press enter. So it gives you this report, right? So you have the classification report. So you see so you have three species: Setosa, Versicolor, and Virginica. So the precision 1.00. Like everything just looks perfect. So you have support, you have 10, 9, 11, blah blah. So for the accuracy now you have macro average, weighted average. So everything is all this 111 tells you like the model is perfect. And that's that's something to be worried about, right? But in this case, the model is perfect, maybe because of the nature of the data set we are working on, right? So, but I mean, let's dig deeper. So let's talk about the report of the results we've got. So everything is one. That's perfect recall, perfect precision, perfect F1 score, perfect everything. But I mean, when you get a result like that, you should be careful. You should be worried a bit to be sure everything is right. Okay, so accuracy score is 1.0, as you can see. So we see the accuracy score everywhere, as you see here. This accuracy score is the overall thing. The accuracy score is 1.0. So the model that means that the model correctly classified 100% of the test samples. That's 30 out of 30, right? Then this is so. I mean, we used 80% of 150, right? Yeah, I think so for the tests. So and 20%, that's 2 over 100 of 150. Um, that's 2 times 150, 300 divided by 300 divided by 100. No, 20%. That's 20 over 100 times 150. That's 2 over 10 times 150. That's 300 over 10. Yeah, that's 30 out of 30, for the test, right? So this is the highest. So the model accuracy classified 100% of the test samples. That's 30 out of 30. This is the highest possible accuracy, indicating perfect predictions on the test set. So we got perfect prediction with the iris data set. But I mean that won't always happen. So to be very sure. Okay. So let's look at the breakdown of what this is about. So for the precision now, out of all predicted samples for a class, how many were actually correct? Okay, that's what precision tells you. So 1.00 tells you 100% was correct. For the recall, out of all actual samples of a class, how many did the model correctly identify? So a score of 1 for recall means that the model identified 100% for all the species, right? The F1 score, harmonic mean of precision and recall. So this balances false positives and false negatives. Perfect score, all right? For the support, that's number of true instances for each class in the test data. So for number of each instance for Setosa is 10, versicolor is 9, Virginica is 11. Then for all these ones now, it's of course 30, 30, 30 for the tests, right? So then we go ahead to look at the per class performance. So for Setosa, Vesicola, and Virginica, talking about the species, all have precision equals recall equals F1 score of 1.0. So perfect class performance. So it's not like, of course, in another using another data set, you may not get this kind of perfect score. In fact, so no miscalculations occurred for any class. That's what this is telling you, getting a perfect score. So perfect performance across all flower types. That's what has happened here. So per class performance. Then for aggregate metrics now, so for macro average, so it means average across all classes without weighting is 1.00. Weighted average, that's average weighted by number of samples per class, is also perfect. This is too good to be true. So you want to be very careful anytime you get a perfect score like this. But of course, the very nature of the iris data set is why the result has come out this way. So in conclusion, right, the KNN model performed flawlessly on the test data. However, be cautious, like I've been saying. So a 100% score may indicate so many things, like a very simple data structure. So like the iris data set, which is often linearly separable. So the iris data set is linearly separable. So you have 150 data points, 50 species each. Times 3, that's 150. So there's also possible overfitting, especially if the data set is small or not well shuffled. Okay, so there's a possibility of overfitting. All right, so then because of that, you may want to consider validating with cross validation or on sync data for more robust evaluation. But I think the most important thing here is knowing how to deploy k k k k neighbors, K nearest neighbor, sorry. Then finally, let's look at tuning K and plotting accuracy. So imagine that we have a task to test multiple values of K, say from 1 to 10. I want to plot the accuracy to identify the optimal K. And so we go through all this process. So to try K values from 1 to 10, so K values range from 1 to 11. Of course, that'll be from 1 to 10 because 11 will be not included. So we are computing the accuracies for each value of K. This is initializing for that. And then for K in K values, now you do the model, K neighbor classifiers, then the model, you do everything we did up there. For accuracy, you have accuracy score, Y test, model predict, X test. For accuracies, you want to append, so you're appending accuracy into this place, into the initialized one, and then you are visualizing. So because of the perfection of the model, we won't see we don't expect to see any drama because it's really straightforward. So you see, whether you have one neighbor or 10 neighbors, the accuracy is always one. So normally we should expect fluctuations like for a regular data set, but for this one it's perfect across board, and that tells you the data is too simple, the structure of the data is too easy. So questions for reflection. So which values of K gives the best accuracy? Uh, well, we don't have everything gives the best accuracy because it's one for everything. So how does the accuracy change as K increases? It's not changing at all. For another data set, it may change. What happens if we don't scale the features? You may also want to check that out. So the summaries and takeaways. KNN is a simple yet powerful classification algorithm, and it is ideal for medium-sized data sets. It is distance-based model, and it requires feature scaling Choice of case critical, so you use cross validation or accuracy plots. No training phase, but prediction is slow for large data. So if you have very large data, it may not work so well. So thank you so much for listening. Let me know how helpful this video is for you. If not subscribed, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. There's also room for membership if you want extra privileges. Feel very free to join the channel as a member. Till I come your way, then be sure to like and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing data right. Bye.